Hello everyone, today I'll show you how you can generate buildings with the PCG Graph system in Unreal Engine 5.4. You can use this method for creating different sizes of buildings with different features on each building to have your city look more randomized and more natural. I have as well added decals with graffiti elements or with leaking moisture from random windows on the building walls. So if I select this building, I have different variables to control the size of the building in each direction. I can control the number of floors, and I can randomize different features on the sides. For example, if I want to not have doors on this building, I can enter 0. Now I have only the garage doors. If I want every item on the first floor to be a garage door, I can enter 1 or repeat them each second wall. Or as I had before, I can have a couple of doors and then random amount of garages on each side. On the main floors, I can have different type of windows. So I have this double window and a single window. If I enter 0, I will not have the double window again. For this window with the closed up bricks type, I can also have it randomly placed or in any type of pattern that I want. If I can have all the windows the same, let's say I'll go back to repeating the double window and the single window, and on the last floor I can have the roof windows which have a special type of door for the last floor. This is based on the Quixel Neo Baroque building type 2. This is the type 1 Neo Baroque building. So if you create this PCG graph, you can easily then swap the meshes and have a different type of building with the same controls. So I can increase the number of floors or decrease them, and I can randomize some elements on the side of the building. So I can have different type of elements on the first floor and so on. Let's go with the first type, and then I'll show you how you can change to another type of building with another set of meshes from Quixel Megascans. It's a bit of a long process to create this PCG graph, so maybe it will be split in a couple of videos to not be too long, but let's start and we'll see how it will go. I will now delete everything in this scene and we'll have a fresh start. Now let's start with creating the blueprint. Let's right click in the content browser, create a blueprint class, choose the type of actor to be able to place it in the scene. Let's call it BP building. And inside this actor, we'll need to have a PCG element. Let's create a PCG component. And for the PCG graph field here, we need to create a PCG graph to connect it. So right click into your content browser, go into the PCG menu and choose PCG graph. Let's call it PCG building. And let's drag this PCG graph into the component in the blueprint that we just created. So drag this into the graph field, compile and save this building blueprint. Now When we create the building, we need to have control over a couple of variables. So let's create the variables now, so it will be easier later to use them. Let's start with creating the variables for the size of the building. Click on the plus sign next to the variables field, and let's start with the width. It should be an integer value. Let's create another variable, call it length. It will be an integer again. Another one, height. It will be again an integer. Now let's create some variables for the generation of each floor of the building. So let's click on this add variable again and create a wall length variable. Let's choose a float type for this. Create another one which will be pillar length. I'll show you now what is each one representing. Create another one, corner length, and one called ceiling height. So having these variables will help us create different buildings with just one blueprint. So make all of them public by clicking on this eye to be able to use them in our PCG graph. Compile this blueprint and save it. Now let's drag this blueprint into our level and let's move it into the position 0, 0, 0. This will make it easier to generate the building, and then we'll modify it to be used on any location that we have. We will go now into the PCG graph to create the logic that will create the first floor, and we'll reuse this for every other floor of the building. So we'll create it as a subgraph, but let me quickly explain what we will do. Let's choose the meshes that we will use for creating the building. So I'll start with using this wall. I'll add a pillar between each wall, and then, as I have, for example, this wall, I'll need a corner element, and then the other side will start from this corner element into the other direction. We need to do this for all the four sides of the building and have it procedurally generated by the settings of how much we want the width to be and the length for the building. I wanted to show you this in order to explain a little bit more visual what we'll do right now. Let me add one shape to explain what's the logic that we will be using creating this wall. So let's say this is the PCG point that we are generating with our PCG graph. I'll scale it a bit to be more precise. So when we create a PCG point, we will spawn from it this wall and this pillar. We'll then find only the corner points for our building. We'll remove the pillar from there because we only want on the edge to spawn this wall. And then when we remove this pillar, we will spawn this other type of pillar for each corner. What is also important to note here is that when you're using this Quixel assets. If you go and place this wall, you will see that the pivot point for the wall is here in the corner, not in the middle. And by choosing to place the walls from the middle, it will be a little bit easier to keep up with the math needed to do the 4 walls. So what we'll do is we'll offset the wall by the half of the length in order to be placed directly on top of this point. So this wall, if you hover on the model itself, you will see the approximate size on the bottom of your screen, which is 400 units wide. So this is the length of the wall which we'll be using for this building. For the other pack of the Neo Baroque building 1, the sizes of the walls are 350. So we have this in a variable. For each building it will be different, but for our current one it's 400. So we'll start with this number and you'll see how later we can change it for any type of building. So by having this wall 400 units wide, we need to offset it by 200 in order to be in the center of this PCG point. Also, we'll be placing this pillar, which is 75 units. So we'll actually need to offset by the half of the total length of this. So 475, half of it will have 232 or something like this. We'll calculate this and offset by half of this width, and that way it will be more easy to place each element on the side of the wall and for them to be connecting properly at the edges. So let's delete this example meshes that we made. And let's start with editing our PCG graph. Let's open the PCG graph that we just created. Now let's start with creating the logic inside to create the walls. First, let's create a point grid. So start typing point grid and choose this create point grid node. Let's set the grid extents and cell size based on the sizes of our wall and pillar. So the wall was 400 units and the pillar was 75. So let's add them together, and this will be the cell size for X and Y, and for the Z the wall height was 400, and the grid extents, let's for now make it 475 by 3. This is a great way to set your numbers by writing expressions in the fields. So don't need to calculate the proper size, just write the expression that you want. So now this grid will create points with this size that we set here in the area that is covered by this grid extents. Actually, for the vertical we can just set it to 400 because we will have only 1 4 for now. We'll make this subgrid to create each 4 points. So let's debug this create points grid field. Let's zoom out a little bit. So this points grid is spawning points into our level. They are with the size that we set up here and covering this area. Let's scale them down a bit by creating a bounce modifier, because now they are overlapping each other. Let's scale the bounce by 0.5 in each direction. Now let's debug this by selecting the node and clicking the D key on your keyboard for debug, or manually enabling this debug option for each node. You can preview the result of this node in the viewport. So now I have this grid of points. It's created with the size of the wall plus the pillar, and then scaled to half of the size by this modifier, so they're not overlapping. Now, what we'll do to create only points on the sides of this grid, we'll move our points half of the size of each cell in the one direction and then in the opposite direction, and we'll just delete the points that are overlapping each other in the middle. So to do this, we'll create transform points node. Half of the size is 475 divided by 2. We'll move them to the one side by this amount. I'll copy it again, move them down the negative amount, and then rotate them because the walls on the other side needs to be facing the opposite direction. So one of the transforms is positively moving to the right and the other one negatively moving to the left, and rotating them to the opposite side. Now let's do a difference node. As a source, we'll put the first set of points, then we'll connect the second one for the difference. Let's stop debugging this and start debugging the difference. You'll see that now we have only one side of the wall, because this is our original point set. This is the one that we are moving to the right. If I enable and disable the debug, you'll see that it's moving the points to the right. If I enable and disable the other one, you'll see that it's moving the points, the original points, to the left. So when we difference these two sets, we are only getting the ones that are not overlapping in the middle. So let's copy this difference node. Let's change the source to the second set and the difference to the third set. So now the second difference is actually creating the other side. So if we debug both of them, now we are seeing that they are creating the two sides of our building. So we'll do the same for the other two sides of the building. So copy the transform points and the difference nodes. You can connect them in the same way. First one for the source in the first difference and for the difference in the second difference node, and the other one for the remaining pins. Now the transforms needs to be in the Y direction, and I'll rotate the first set 90 degrees, because on the other side of the building we need to have the walls facing the other way, not to be parallel with the ones on the sides. For the other side, we'll rotate them negative 90 degrees and move them in the Y axis minus half of the size. So now if I connect everything, if I stop debugging this, these are the original points. I'm moving them forward with this first transform, moving them backwards with the second, and the two different nodes are creating the two front and back sides. Combined with these two different nodes, I have the four sides of the 4 to spawn the walls and the pillars. So let's stop debugging. And now, because everything is set with a static number here inside our nodes, it will work only for this particular size of elements. And we don't want this. We want our subgraph to work for any building that we create. So let's start populating these fields. I just wanted to show you how this is working, so you understand everything and are able to debug if there's any problem on your graph. Let's start by into our graph. Let's actually make this into a subgraph. So select everything here, right click and collapse into a subgraph. Let's save this subgraph here where the other graph that we are creating is made and call it PCG subgraph 4 or single 4 to be more precise with the naming. So now our PCG graph only contains this single 4 subgraph and it's doing exactly the same thing as before. Let's double click into this single 4 subgraph or find it in your browser and open it from here. We have the same thing here. The difference is that now I'm going to create some parameters here. So click anywhere on this empty space, so you don't have anything selected, or click here onto the graph settings node on top, and into the parameter fields create a couple new parameters. So I'll create, I believe 6, or 7. I think we need 7 for now. So the first one will be the length of our building. The second one will be the width of our building. We need the height of our building. Then we'll have wall length. Then pillar length. Then we'll have the ceiling height. And we can create one field for the cell size. This will be combining the length of our wall and pillar. It will be easier to connect everything inside this way, or we can just calculate it inside. Let's remove this cell size. We'll use for now just these 6 parameters. So the first 3 needs to be an integer. So let's change the type for all of them from float to integer, and the other 3 can be a float value. So let's save both of our graphs. Let's give our parameters a default value. So the length of our building, let's say it will be 4 walls by the length of the building. The width will be 3. The height, for now, it will not do anything because we are doing a single 4, but let's say 5. The wall length will be 400 by default. The pillar length will be 75 and the ceiling will be 400. These are the default values for the building that we are creating now. They can be overwritten for different type of meshes, for other sets from Quixel or other meshes that you have for your buildings. But I'll start with these default values. That way will be easier to debug everything when we have default values that match our elements. So the first thing that we can do is use this parameters when we are creating the point grid. So the grid extends field, you remember that I created it by multiplying the width in an integer value. So I multiplied 3 by this size. So let's first create this cell size variable. This will be our wall length. So start typing wall and you will get this wall length variable. It's currently set to 400. Let's add it. So drag out of it and type an add. It will create a math operation addition. So make sure here it's set to add. Now right click anywhere and start typing pure. It will give you the pure length variable. So when we add this wall length and this pure length, we are getting the cell size of our grid. So this 475 we will get from the addition of our two elements that we set up by these parameters. So the grid extends needs to be our width and our height multiplied by this cell size. So the width we'll drag and do a multiply by this cell size, and we'll copy this multiply and do it again for the height. I'm sorry, not for the height, but for the length. So type length and choose this get length parameter. So connect this and multiply it by the cell size. And now drag out of one of these multiply nodes and make a vector. The type of vector we need to change to regular vector with 3 values. The x value will be the multiplication of the width and the cell size, and the y value will be the multiplication of the length and the cell size value. Then for the z, we'll just get the ceiling height and set our z value here. Now let's connect this to the grid extends. And in this way, we're making our grid generation based on the values that we set up in our parameters, and not just statically set up every building the same size each time. So now we have control over the size of the building that we create. So if we debug now this bounce modifier, you see that one of the sides is bigger than the other because we have the width of the building set to 4 and the length of the building set to 3. So now we have a different size for the two sides of our building. So now let's stop debugging this and let's start making these transform points use the parameters that we just created and not to be set up statically like it is now. So this 237 is actually the cell size divided by 2. So the cell size is this result here, the wall length added to the pure length. Let's copy this here. Let's divide the result of this by 2. So drag out of here, write divide, and for the second pin here, right click somewhere and add parameter, add attribute, sorry. And the attribute will give it a value of 2. So we'll divide by 2. And the result will make a vector like we did before. So make vector. The vector will be vector 3 values. And now this vector will connect to the first transform points offset min and offset max, you will see the offset min and max is this value for half of the cell size. So let's connect this here. Let's collapse this. And for the second one, we need the same vector, but this should be a negative 237. So when we divide this, we need to multiply the result by -1. So let's copy this at attribute and type -1. So we have 275 here, and now 237, sorry, here. And when we multiply it by -1, we have negative value, and we'll make another vector, which is with the negative value, and connect it to the other transform points. So now, if I show you everything, let's select this divide node, click the A key, then go here and select this subgraph. When we select the subgraph to debug, everything becomes disabled, so it shows that there's some error and it's not working. So actually here in the 5.4 version they changed this behavior, so this at attribute needs to be connected to some points, and we don't have this. So we need to create attribute instead. So the value here is 0.5, actually 2. Let's copy this, and the value should be -1. Okay, so now everything is working fine. Let's select this divide node. Actually, let's select this add node. So first, when you select here the subgraph and you click the A key for this add node, you'll see that it's calculating properly the wall length and the pure length together to 475. Then we are dividing by 2, so let's change here the A key to the divide node, so 237. Now this multiply is -237. This vector has an x value of 237 and y and z to 0. So we are mimicking the behavior that we had before. X is 237 and the others are 0. This second vector is -237. So the same thing here. So now for the third and fourth transform points here, you can see it's the same thing, but the values are in the y axis. So copy this make vector twice, and for the first one connect the positive value to the y, and for the second the negative value to the y. Let's move these things, and now the transform points offset. For the first one we will have the positive values, and for the next one the negative values in the y direction. And now if I debug all the difference nodes, I have the same result as before. I have the 4 walls points, each in the direction that I want. You cannot see the directions here because they are just cubes, but if I change the debug option here, not to the cube but to the axis tripod, you will see the arrows pointing. Let me just move this a little bit up. We need to move our points up because they are currently below the floor. So for each of these transform points, select all 4 of them, or actually just here we have the offsets for all of them. So let's use the ceiling height. So ceiling height variable that we have, let's divide it by 2. So copy this divide node and this value of 2. And let's connect this ceiling height to all of the Z values. Oops, sorry. Okay, now we have them on the floor. So you will see that the rotation that we added to these transform points, it's making sure that for each wall this red arrow is pointing in the outside direction. If we don't rotate the points, for example, here on the second one, if we leave it at 0, we'll have a problem where our walls here on the left and right, they are each pointing to the right. So when we create the walls, the outside of the walls will be inside the building here. So that's why we are rotating here 180 degrees, and these 2 transform points on the bottom we are rotating 90 and minus 90 to have the other 2 walls facing the same direction. So now that we have all these points for the walls, let's continue with making points for the corners. For the corners of the building, let's combine these first 2 walls. So let's debug only these walls. So let's do transform points for this. Transform points. This is creating this node that's converting to points the result of this difference. So connect both of these first 2 differences, so these 2 walls, to this transform points node. Connect the bottom ones to another transform points. And let's move these points with half of the value of our cell size. So because we are using this cell size in a lot of places, we are calculating it here. Oops, sorry. We are calculating it, yeah, here. So let's drag out of this add node and start typing add named reroute and choose this add reroute declaration node. Then right click and choose rename and write here cell size. So now if we drag out of here, we can always use this cell size like it's connected to this node here. So here where we had this addition in our divide node here for the transform points, we can just use this reroute node. So right click and choose the cell size node. And now where we need it here, right click again, choose this cell size. And we need to divide this by 2. So divide, make, create attribute, this attribute will be 2. We'll divide by 2. We'll make a vector. The vector will be with 3 values, and we'll connect it to our offset min and max for both of our transform points here. And actually we'll connect it to the y value, not the x one. So now we have half of the length for our cell size transform here for each wall. So you'll see that if I debug this first transform points, it's moving the points to the side, and for each wall it's different side because they are rotated 180 degrees. And if I debug the other node, you'll see that it's moving them again in the opposite directions. So now I'll do an intersect between the moved points and the original points of the two different nodes here. So let's do an intersection. Let's debug this intersection, and you'll see 2 points for the 2 corners that are created, and of course we'll need another intersection where we'll intersect the result of this transform and these original points here. So if I debug the other one, we have the 2 other corners, and if I debug both, we have the 4 corners of the building. If I show you the results that we have the 2 walls on one of the sides into this first pin, the 2 walls for the other side in the other one, the 2 corners in this first intersection, and the 2 other corners in the second intersection. So let's move the corners up. Now we'll create for the corners transform points. We'll connect all of them. So these are all of our corners here. Let's debug this. These are our 4 corners, and we have a transform points to modify them. And let's merge these points for all of the 4 walls, and let's split from these merge points to create 2 transform points operations. The first one will be for the pillars, and the second one, let's copy it, it will be for our actual walls. So let's stop debugging this. Let's start creating here the logic for the transform for the pillars and the walls. So as I showed you before, when we create a wall, let's go back to our walls. When we add a wall in our level, it's placed based on this pivot point, and the points that we are generating, we want the placement for the wall to be in the middle of the wall with the pillar next to it. So what we need to do for these transform points is again calculate the transform that we want to apply with these offset values in order to have the wall placed over the point that we are using to generate it. So let's use our wall length. So right click and start typing wall and choose the wall length parameter. Let's multiply this, or let's divide this by 2. So let me copy from somewhere Okay, this create attribute 2. So we are dividing this wall length by 2, and then let's add to our wall length the length of our pure. So start typing pure and add the pure length variable here. So now we'll add the pure length to half of the wall length, and we'll use this to make vector attribute. We'll actually connect it to the y value because this is the side-to-side movement of our wall. We'll change this to a vector with 3 values, and we'll move in x with the amount that our pure width as well, because when we stack walls next to each other, like on the corners, we need to account for the pure size to make a room for the pure between the two walls. So we'll add our pure length here for the x value, but we'll multiply it, we'll divide it, sorry, by -2. So we'll have the negative value of half of our pure width. I'll show you what this is making to our points. So let's connect this into our offset min and max for the pures, and then let's spawn static mesh spawner. Let's choose the mesh entries. Let's add another one. Let's choose the descriptor, and here into the static mesh, let's choose our pure. So drag this pure into our static mesh field. This is the corner one, so this one. Let's drag it into our static mesh. Let's delete the walls that I used to show you. So the pures are actually not facing the right way. So these transform points we'll also use to rotate them -90 degrees. Okay, so now our pures are placed between each wall, and here when I'm dividing this pure length by 2, if I divide it by 1, so it's actually, let me spawn the wall and I'll show you. Let's put a -2. Now let's do the same transform for our walls. So we'll use this pure length and this wall length, so divided by 2. So let me rearrange some things. So let's make another vector. It will be a type 3 vector. I'll connect this here. So for the walls, we are moving them half of the wall length on the side, and then half of the pure length to inside of the building. So let's connect this here into these transform points. Offset min and max. Let's copy the static mesh spawner, and let's spawn not the pure but the wall instead. I need to rotate the wall, so minus 90 degrees for the wall as well. Okay, now I have the wall and the pillars. Actually, because you can see on the corners they're overlapping too much, I don't need to move them to the inside. I'll change this to a positive 2. So now we just get half of the pillar length and moving our wall outwards with half of the length. So if I mark this make vector, click the A key and select the subgraph here, you see in the x-axis we are moving it with half of the pillar length to the outside. So we have a place here to place our corner. And the only problem is that we are spawning a pillar in each corner that we don't need. So for our pillars here, before we spawn them, we need to add a difference node, and we'll use these pillars as a source and the corners that we got here. So connect these corners to this difference node, disconnect the spawning of the pillars and connect it again. So now we should be able to remove the corner elements here. So it's not working because we need to edit the bounds before we do this. So bounds modifier. Our corner points are currently not big enough to be able to do this operation, or maybe we just change the operation to binary, so it will be enough. Okay, so we get this result with just changing the type of the density function to binary. Otherwise we could make the bounds bigger and it would work, but we can change this to binary and it will work better now without changing the bounds to our corners. So let's stop debugging the corners. And now we are placing all the pillars and the walls. We just need to place the corners. So after these transform points, let's copy this static mesh spawner. Let's choose this corner pillar and add it to the mesh entries. And let's connect these transform points here. So the problem is it's not spawning directly in the corner. We need to transform it by minus 75 divided by 2, okay? And in the other direction, we need 75 divided by 2, I believe. Yeah, so you can see these are the negative half of the pure width and the positive half of the pure width. So we have this, the pure divided by 2. So let's copy this. Let's paste it here. Let's copy it again and paste it and get the negative result for one of them, the positive for the other. The negative should be in the x vector, so make a vector, change it to type of 3. The positive should be in the y, and now connect it to the offsets min and max. And now we are spawning the corners. We are spawning here the pillars, and we are spawning the walls if you mark any node and click the E key, it will enable or disable. E for enable. So you can easily test what each spawn mesh node is doing by marking it and clicking E to disable it. So we are placing each wall, each pillar, and each corner with these nodes here, and the size of the building is directed by the variables for our width, length, and the size of our wall and pillar. If I save this and if I go back to the original PCG graph, which contains this subgraph currently, only this subgraph. So now if I open the blueprint where we created these variables, width and length and height, if I go to the original PCG graph, get actor property, and for the actor property name, add the name from your blueprint. Let's get the width, the length, the height, the wall length. Let's copy them to not do a mistake. Now the pillar height, pillar length, sorry. We are not using the corner length, we are using the ceiling height, so let's get the ceiling height as well. So now we have all these properties here into our graph. Let's open this subgraph and let's start in connecting. This is the width. You can see here in the orange header, it says what property you are using. So this should be the width, this should be the length, this is the height, this is the wall length, this is the pillar length, and this is the ceiling height. So let's save this. Let's compile and save this graph. Again, make sure that you have default values set up here for all of these variables. This is 3 for the width, length, and height of our building. The wall length is 400, pillar length 75, and ceiling height is 400. So now, if I delete this blueprint, when you put the blueprint in your level, it will generate based on these values. And if you change them, it will change the size of your building. Currently, if I set the size to 2, it's generating more walls. So let's check what we are doing inside our single floor. So we are getting the length, we are multiplying by this cell size. We need to get half of this value. So let's get half of this vector. So multiply this and add attribute, not add, but create attribute. Now let's do a 0.5, multiply by 0.5, or you could do divide by 2. So this will connect into our grid extents value. Let's save this. And now when we're in our level, we can control the length. Okay, now I have properly 3 units of length. The width, I have properly 4 units. So now you can place the blueprint and generate a single floor. I believe that we are heading to over an hour currently, so I'll end this tutorial for now with the generation of a single floor, and in the next tutorial I'll show you how you can use this floor to generate. First, maybe we'll start with the variation of the elements on the first floor, so we can add doors or different type of walls with garage door, something like this. And then we can proceed with creating the other walls, the other floors, sorry. And at the end, we'll generate the roof and add the decals to make the building look more natural. And after this, we can start modifying this blueprint to work with other assets. Like I showed you, I have the different Neo Baroque building connected, and you can generate different buildings with the same blueprint. So for now, that will be everything, and if you have questions or some problems, please write in the comments, and I'll see you in the next video. Bye!